Hello, I'm Emily Happy. I'm here with,
Vincent Andrews.
I'm Emma Sandidge.
and we are team number 1013 from Florida Institute of Technology. Our coach is Anthony Stefan, and we chose problem B, the mechanics of suction feeding. So in this presentation, we're going to go through and define the problem. We explain the assumptions that we made, explain the model that we created based off of those assumptions, and we describe any limitations that we encountered and some further applications that we made. So the problem itself, we were presented with the suction feeding method. So we developed a mathematical model of jaw movement. We estimated the minimum time it takes for the mouth to open and close, and we explored how effective and what the range of this feeding technique is.
So before we begin modeling our problem, we made some assumptions to simplify our model. So from the PDF of the assignment, we found that the mouth parts had simple attachment points at their ends and that the fluid interactions did not affect the motion of the jaw. From that, we also assumed that the system was two-dimensional, as the fish was just moving in one direction towards its prey. And then we assumed that the muscle region was subject to 5 main muscle components, which we'll mention later. And then we assume that the number and size of the prey is also constant in the problem, and that the jaw can be modeled periodically since its jaw had fixed endpoints at the ends, and then we also assumed that the buoyant force and gravity cancel out so that the fish was not moving up and down, affecting the displacement. So for our model, we got this image from the source provided to us on the left, and it shows the largemouth bass with its mouth closed and then open, and it highlights the 5 major muscle components affecting the motion of suction feeding. So we have the lower jaw, the pectoral girdle, the composite hyoid, and then the maxilla and premaxilla muscles. And we noted here at the bottom that the force was maximized at the fixed endpoints of the jaw when the highest vertical displacement was reached, Y max. And we noted that the time that this would happen would be T max over 2, where T max is the full period of the oscillation.
Now we move on to creating the differential equation. So our function will model the vertical displacement of the jaw, which means how much it has opened with respect to time. We pictured the fish's mouth opening and closing similarly to a periodic function, and because the mouth parts were assumed to have simple attachment points, we utilized simple harmonic motion to fit our model. The following variables will be used in the equation. M is the mass of the predator. Beta is the damping force, which in our case is due to water resistance against the jaws. Y of t, our function, measures the vertical displacement. And the variables K1 through K5 are the respective forces of the jaw muscles. The following differential equation is modeled below, along with the constraints that the muscle forces are positive, the mass of the predator is positive, and time begins at T0, which is 0. We also have the initial condition that our function is 0 at T equal to 0, because the predator's mouth will be closed at the start.
So some of the structure limitations that we encountered, that the feeding is based on the time it takes a predator to open its jaw, suck the prey in, and then close the jaw so the prey cannot escape. So it's based on whether or not the prey can react fast enough to get far enough away from the predator before the mouth closes. So if the reaction time of the prey is faster than the time it takes for the predator's jaw to fully open and close, the predator loses its prey. The predator must be very close to the prey in order to effectively catch it. And the prey must be smaller than the width of the predator's jaws at its widest, or else the prey will not fit in the mouth.
Now, in reality, the muscle forces will not be constant throughout the process of the mouth opening and closing, which is why we represented them as variables. But when they are variables, the differential equation becomes much more complex and difficult to solve. So in an effort to visualize a simplified version of the equation so we could portray a solution, we assumed the damping force to be 0 and let the muscle forces be constants. So the condensed equation is as follows, with the capital K equal to the summation of the individual muscle forces K1 through 5. So the differential equation is simplified into a second order linear differential equation that can be solved using the shown characteristic equation. So the following characteristic equation shows that mu squared is equal to negative k over m. So the chosen solutions will be sine and cosine functions. And then we applied the initial condition to show that C2 must be 0 in order for the function to be 0 at the start, which gives us the solution only with the sine portion. And we restricted the value, the argument of the sine function, to be less than pi. Now we can solve for t by applying the attributes of the sine function to find a value that corresponds to the maximum displacement of the mouth. So when the argument of sine is equal to pi over 2, the function is maximized. Setting the argument equal to pi over 2 yields the t value of pi over 2 times the square root of m over k, where k's are force constants. And this value of t corresponds to the maximum vertical displacement, meaning the jaws are fully open. And to get the total time for the mouth to open and close, we can multiply this value by 2, giving the total time to be pi times the square root of m over k. And an estimate of the shortest time frame for the mouth to open and close will be less than the Tmax value, but it will also be greater than the reaction time of the fish if the feeding method is to be successful.
Since we modeled our equation using simple harmonic motion, we also had to consider the damping force. Now, we solved for one solution where it was 0, so we wanted to consider how the damping force would affect the system and how it would affect the suction feeding technique. So if we go back to the differential equation that we had and divide over by m, we can simplify it a little bit and set the angular frequency equal to k over m, and then rewrite our differential equation as follows, where zeta is the damping frequency. So over here, we noted that the system must be undergoing critical dampening force since the mouth immediately opens and then closes. Physically speaking, it makes sense for this to be happening since the goal of suction feeding is for a predator to very rapidly open and close its mouth to draw prey in. So the oscillation would happen very rapidly and would not continue moving on.
So some other further analysis we had, if we knew the true values of the forces of each muscle in the jaw, the mass of the predator, and the damping force, we would have been able to get a numerical value for the total time it takes a predator to fully open and close its jaw. Some next steps might include creating a 3D model using the area of the mouth and the volume of the water entering the mouth. It might be more accurate if we wanted to measure the amount of prey a predator can consume. And so some acknowledgements. We wanted to thank our coach for encouraging us to enter this competition and compete, SIMIODE for giving us the opportunity to complete this challenge, and then the judges at SCUDEM for reviewing our presentation. And this is our reference that we used from the source provided. Thank you.